So we have our last example, which is really complicated. We're taking we're mapping the real n by n matrix, the real 2 by 2 matrices to R2. And here, the new transformation of A is going to be the integral from 0 to 1 of trace A plus A12x plus A21x squared dx, comma, A1 plus A2 plus A3 plus A11 plus A12 plus A21 plus A22. And this sum here is sometimes referred to as the grand sum. And it has limited uses, but it does have some uses, which is kind of interesting. Now, when we want to show that it's a linear transformation, and here this is going to be left as an exercise to see, can I show something really complicated does in fact form a sum? And you're going to take two general matrices, two general scalars in the real numbers, and determine that AV1 T applied to AV1 plus BV2 is in fact equal to AT of V1 plus BT of V2. Now what we're going to focus on is computing the matrix representation kernel for the basis for our linear transformation and the image of our linear transformation. Let me give the kernel of T. So to compute the image, we're going to look at T of E11, which is T applied to the matrix 1, 0, 0, 0. The standard basis for matrices, the first entry tells me the row, the second entry tells me the column where the 0 entry is. Everything else, or non-zero entry, or the 1 entry, everything else is 0. So this is going to equal the integral from 0 to 1. Now the trace is going to be 1 plus 0 plus 0x plus 0x squared dx, comma, 1 plus 0 plus 0 plus 0, which equals the integral from 0 to 1, 1 dx, comma, 0, which you can see is going to be 1, 0. Now, when I look at T applied to E1, 2, this is going to be T applied to 0, 1, 0, 0, which is going to be the integral of 0 to 1 of 0 plus, and if we go to our linear transformation, A12 is multiplied by x. So this is going to be x plus 0x squared dx, 0 plus 1 plus 0 plus 0, which equals the integral from 0 to 1 of x dx, 0, which equals 1/2, 0. And now if we look at what T does to, oh, these aren't 0, these should be 1s. One, 1. Now if we look at what happens to E21, we get 0, 0, 1, 0. We're looking at what T does to this matrix. We get that it equals to the integral from 0 to 1 of 0 plus 0x plus x squared dx, 0 plus 0 plus 1 plus 0, which is equal to the integral from 0 to 1 of x squared dx, 1, which equals 1/3, 1. And finally, we're looking at what T does to E22, which is T of 0, 0, 0, 1, which equals the integral from 0 to 1 of 1 plus 0x plus 0x squared dx, 0 plus 0 plus 0 plus 1, which equals the integral from 0 to 1 of dx, 1, which equals 1, 1. So combining these together, and I'll just make this bigger, we get that T of alpha beta is equal to 1, 1, 1/2, 1, 1/3, 1, 1, 1. Now we have our matrix representation. From here, we can compute our kernel. So to compute our kernel, what we're going to do is we're going to take our matrix representation, 1/2, 1, 1/3, 1, 1, 1, and create a homogeneous system of equations. And we're going to solve for the solution space for the homogeneous system of equations. So first we create our echelon form. So R2 minus R1 replaces R2, giving us 1, 1/2, 1/3, 1, 0, 0, 1/2, 2/3, 0, 0, R2, 2 times R2 replacing R2 gives us 1, 1/2, 1/3, 1, 0, 0, 1, 4/3, 0, 0. And now R1 minus 1/2 R2 replacing R1 is going to give us 1, 0, minus 1/3, 1, 0, 1, 4/3, 0, giving us the equivalent system of equations of A minus 1/3 C plus D equaling 0 and B plus 4/3 C equal 0. And now that we have our equivalent system of equations for our solution space to this homogeneous system of equations, let V be in the solution space. So if V is in the solution space, then V equals A, B, C, D, and our basic variables are going to be A and B, and my free variables are going to be C and D. So we let C and D, or C equal T, an element of the reals, and D equals S, an element of the reals. Then A equals 1/3 T minus D, and B equals minus 4/3 T. So V equals 1/3 T minus S minus 4/3 T, T, S, or V equals T times 1/3 minus 4/3 1, 0 plus S minus 1, 0, 0, 1. So our solution space, this tells us that our solution space equals the span of the set of vectors 1/3 minus 4/3 1, 0, and minus 1, 0, 0, 1. Well, to get the kernel of T, we need to convert these vectors into matrices using the coordinate system. So if V of alpha equals 1/3 minus 4/3 1, 0, this tells me that V equals the matrix 1/3 minus 4/3 1, 0. And if V alpha equals the coordinates vector minus 1, 0, 0, 1, this tells me that V is going to equal the matrix minus 1, 0, 0, 1. So the kernel is going to equal the span of the set 1/3 minus 4/3 1, 0 minus 1, 0, 0, 1. And this set here, this is my basis. Okay. So we'll move this down one last time. Whoop. Whatever I just did, let's undo. Oh, apparently I can't undo it. So let's, oh, there it is. So let's take this here. And we'll move it down. So my basis for the kernel of T is the set 1/3 minus 4/3 1, 0 minus 1, 0, 0, 1. And now we're going to be looking at creating a basis for the image of T. And to create a basis for the image of T, we look at our column vectors that we had for our matrix representation of 1, 1, 1, 1/2, 1, 1/3, 1, and 1, 1 equaling 0. And we want to span the column space. So we want to look at the column space equals, and it's going to be the span of the set containing the basic variables, or the vectors related to the basic variables from this system of equations. And our basic variables are A and B, so it's going to be the first two vectors, vector A, vector B. So it's going to be the span of the vectors 1, 1, 1/2, 1. Now to get the image of T, what we're going to do is we're going to take these vectors and represent them in beta. So V, if V of beta is equal to 1, 1, then V equals 1 times 1, 0 plus 1 times 0, 1, which equals 1, 1. And if V of beta equals 1/2, 1, then V equals 1/2, 1, using this same approach. So we get the image equals the span of the set of vectors 1, 1, 1/2, 1. And our basis for the image of T is set 1, 1, 1/2. And we can see that at no point did we do anything complicated. And in fact, if we want to know what our linear transformation is doing, we can just look at this matrix representation. And we can just take whatever matrix we have, represent it in the coordinates vector, A, B, C, D, and then multiply it by this operator. And we don't have to go through the complicated mess of determining this ugly expression. Remember what our 4 steps are. These 4 steps that we have here will be the same every single time.